Hello again, Physics 30s. In today's lesson, we are going to take the results from the Frank-Hertz experiment to provide an updated model of the atom, that being the Bohr model. And then we're going to use the Bohr model of the atom to explain the absorption and emission spectra and also the Blackbody radiation curve. Learning outcomes are to explain qualitatively the concept of stationary states and how they explain the observed spectra of atoms and molecules. And two, calculate the energy difference between states using the law of conservation of energy and the observed characteristics of an emitted photon. Okay, so we're going to start off by talking about Niels Bohr. You can see the year, 1912, is after when Max Planck made this quantum hypothesis regarding the wave-particle nature of light. He starts his model off just by looking at hydrogen. And the reason we're going to look at hydrogen is because it's simple. A hydrogen atom has a nucleus with one proton, and you have a single orbiting electron around it. He predicted that somehow the structure of the atom was related to the emission spectra of hydrogen gas. And again, the emission spectra is the bright line spectra. So that's what happens when you put an electrical current through an unexcited gas like hydrogen. You excite it, and then you get some distinct bright lines on a dark background, which I believe is 4 lines in the visible spectrum of color if we're talking about hydrogen gas. So we're going to look at 3 postulates that he makes, and then afterwards we'll use the postulates to look at the spectra of light. Number 1. Electrons move in circular orbits that we call stationary states, but they do not radiate energy. Okay, a bunch of things about this statement. So, number 1, we're not going to refer to them as excitation states anymore. We'll call them secondary states. 2, I don't know why he calls them stationary states, considering how in the postulate he just identified that they're actually moving, but this would require me to do research to figure out why they're called stationary states, and why would I do research when I could play Mega Man? And then number 3 is we still have this problem where, and this is where the Rutherford model of the atom failed. So if we look at the hydrogen atoms, we have our single proton, and then we have the orbiting electron. And we know that an electron that's in circular motion would have some centripetal acceleration, which is towards the center of the circle. And if I have centripetal acceleration towards the center of the circle, we know that an accelerating charge emits EMR. So here's my EMR photon. So as long as this guy is accelerating, it emits EMR. So it gives off energy. If it gives off energy, the electron itself loses kinetic energy, and then it would spiral into the nucleus and then blow up. So we would not have an atom then. So he doesn't really address this problem. He simply just states, yeah, they move in circular orbits where, yeah, there is centripetal acceleration, but they just don't radiate energy. I don't know why, but clearly they don't. Otherwise, we would not exist. So this is something we're going to have to explain in the next lesson in terms of why does an electron not emit EMR. So all he's doing right here is just saying, yeah, I acknowledge that they should, but they don't. 2, of all possible orbits around the nucleus, only a few of them are allowed. So what this means is there's only specific positions from like the nucleus that an electron can actually exist. So it can't exist at any point from the center of the nucleus. We addressed that a little bit in the Frank-Hertz experiment, where we talked about either an electron is at an excitation state or it isn't. It can't exist in between states. Each of these orbits has a characteristic radius and energy. So let's look at the radius first. The radius for an electron in orbit around hydrogen can be calculated by Rn is equal to n squared times R1. Now in this equation, R1 would be the radius of the orbit where you would have the electron, the first stationary state, which is the ground state. So R1 is the ground state orbit, 5.29 times 10 to the negative 11 meters for hydrogen. N would represent the stationary state that you're interested in. So N equals 1 would be the first stationary state or the ground state. N equals 2 would be the second stationary state. N equals 3 would be the third stationary state or orbit. I suppose the one thing to note in this equation is that there is a direct square relationship between the Rn and n squared, which means that the further you get away from the actual nucleus in terms of your stationary state, the orbits are going to be located progressively further and further away. And by further away, it's going to occur in an exponential manner. And yeah, I've already identified this. N just represents the nth stationary state. So the one good thing about calling them stationary states is the first stationary state is n equals 1. The second stationary state is n equals 2. The third stationary state is n equals 3. Unlike with the Frank-Hertz experiment, we had that the numbers being offset, where n equals 1 was the ground state, n equals 2 is the first excitation state, n equals 3 was the second excitation state. So by calling them stationary states, at least we can eliminate that problem. And yeah, just to kind of give like an illustration of what this would look like. So this orbit here would be n equals 1. This one would be n equals 2. This one would be n equals 3. And what I can see is that the spacing is progressively getting bigger and bigger and bigger between the orbits. And again, that's due to that direct square relationship between the orbit, the radius of the orbit, and the stationary state that you're actually looking at. E, the ionization energy. So once again, physicists like for every reason. And again, this would require me to do some actual research to figure out why they like ionization energy so much. But again, I'm not going to do it. They like to measure energy from the perspective of ionization, which means it's the hypothetical question like, how much, if an electron is in this orbit, how much energy would I need to give it in that orbit to leave the atom completely? So the equation we have here is En, so that'd be the ionization energy in the nth stationary state is E1 divided by n squared. So E1 is negative 13.6 electron volts. And we looked at this this diagram in the previous lesson for the Frank-Hertz experiment. So what this means is that if you do have an electron in the ground state, from the perspective of ionization, I would need to give this electron 13.6 electron volts to completely leave the atom. And again, the reason I think of it as being a negative number is because the electron has not been given that amount of energy at that point. It's just sitting in the ground state. So it's kind of deficient in that amount of energy to get it to be ionized. Or we can write it in joules as negative 2.18 times 10 to the negative 18 joules for hydrogen. The relationship here between the ionization energy and the stationary state you're looking at is a inverse squared relationship, which means that at the higher stationary states, you need less ionization energy. And that's not surprising because you're closer to the electron, because at higher energy states, you have more energy. At the second stationary state, n equals 2 here, you already have 10.2 joules of 10.2 electron volts of energy. Therefore, you only need 3.4 to actually get the thing to leave the atom. 3, electrons can jump from one orbit to another, but they cannot exist between them. I put jump in quotation marks because, again, it's totally unclear as to how they go from one stationary state to another. Like, do they teleport? Like, what do they do? All we know is that they instantaneously jump. They can't exist anywhere between these different orbits. So again, going back to this illustration, it is not possible for an electron to exist in this state. This might also explain why the spiraling can't occur, because if the spiraling could occur as a result of giving off EMR, that means as it spirals, it could exist in between energy states, and as we know it can't. Oh, look at that nice horizontal line there. I love drawing tablets. Okay, when an electron absorbs energy, it jumps up to a higher stationary state, or excitation state, if you want to refer to it like that. And then the thing with these electrons is that they're lazy. I mean, don't get me wrong, they're not sentient. I'm just going to pretend like they're actually lazy. So they always want to go back down to the ground state because the ground state is like the lowest energy state. So when they jump down, which they're going to do, whatever energy they absorb in going up, they then emit it in the form of a photon as they go back down. So the energy emitted or absorbed has a frequency or wavelength that we can determine from one of the following equations. So if we had an energy level diagram, maybe I could actually go back to like the previous energy level diagram. Yeah, let's do this. Okay, so let's go back to this one. Okay, so let's say we're going to make a jump from n equals 2. Let's change the color here. Let's go to red. Okay, n equals 2, and we wanted to go to n equals 1. It's when we jump down that we emit a photon of light. This is actually going to be an ultraviolet photon. I'll just draw it in red here, but it would be a UV photon. Okay, so if I want to calculate how much energy of a photon is being emitted, I can actually use the values from the different energy levels to do this. So my initial state is the higher state I start at. So in this case, this would be EI. So that'd be negative 3.4 electron volts. And if we jump down to the ground state has ionization energy, EF, of negative 13.6 EV. So what I can do is to calculate the energy of this photon, so we can call this E. This E would just be the difference between these two different energy levels. So this would be like EF minus EI. So that would be negative 13.6 electron volts minus negative 3.4 electron volts. Now that's going to give you a negative number, so I would just put the absolute value sign around that. And then I believe when you do this, it would give you like negative 10.2, but we just take the absolute value, be 10.2 EV. So that's how we can use the different the ionization energies from the different stationary states to predict what energy of a photon is being emitted. So if I go back to my equation now, it should make more sense. So this would be the energy of my photon, delta E, or I said delta because it's a change from like a final to an initial state. And again, the final is always going to be a higher state. And the I is going to be a lower state. I'd probably just call this E though. Final minus initial, take the absolute value. And then if I wanted to, I could calculate the photon frequency using Planck's formula, H times F, or you could also use E is equal to HC over the wavelength to get the wavelength if you're asked to do it. There's another equation we can use to calculate the wavelength of an emitted photon. So we have 1 over lambda is equal to RH, 1 over NF squared minus 1 over NI squared. So that's for an emitted photon, the wavelength. So RH is Rydberg's constant, so 1.10 times 10 to the 7 meters to the negative 1 for hydrogen. This equation should be ringing a bell a little bit. I believe it was the Balmer equation, which just predicted the 4 wavelengths for visible light and hydrogen. I think it looked like the exact same thing, except this was a 2. It was 1 over 2 squared, minus 1 over Ni squared. Well, we can actually make physical sense of this now. So let's go back to, again, the energy level diagram for hydrogen. I'm just going to erase all this because it's starting to get a little bit messy. Okay, so I have this equation that I can use to calculate the wavelength of an emitted photon as it jumps down. So we have RH, and then I have 1 over NF squared minus 1 over Ni squared. Now the Balmer equation, and again, the Balmer equation didn't make any sense of this. It simply is a mathematical equation that predicted the first 4 wavelengths of visible light for hydrogen. So that equation looked like RH is equal to 1 over 2 squared minus 1 over Ni squared. So what the N represents is NF would be the stationary state you're jumping down to, and I be the stationary state that you're starting at. So if you look at this equation here, well, this would be an NF that is equal to 2. And we showed in that previous lesson that depending on the jump, if you make like a jump from, for example, let's say Ni equals 3, so an electron jumps from here down to there, you emit a photon that I believe gives you a wavelength range that's going to be red. And I think all the jumps from whatever, like we could go from 3 to 2, or we could go from Ni is 4 to 2. So if we go to 4 to 2, I think this one might emit, I was going to say correct me if I'm wrong, but you can't correct me if I'm wrong because I'm just talking into a microphone with no live audience. You get a green photon. Or if you did another jump, if you went from Ni is 5 to NF is 2, I think then you start to get blue or like an ultraviolet one. So that's where we get a lot of like, for hydrogen specifically, those first 4 visible emission lines for hydrogen always involve you jumping down to state 2. So at the time, Balmer didn't really understand why this was a 2 because it had no physical meaning then. But according to the Bohr model of the atom, they do have physical meaning now. Like N is a reference to the stationary state that you're looking at. Again, NF would be the higher state, Ni would be the bottom one. And any jump to an NF value that's 2 is going to result in some kind of production of a photon that's in the visible part of the spectrum. In fact, I believe that they call those lines for hydrogen the Balmer lines specifically just in reference to the equation he made, and also, the equation he made in just the first, the visible lines of hydrogen you can actually see. Okay, so yeah, we have this equation, and again, this equation, we don't have to use 2 here. We can use whatever value we want for jumping down to a state. But the one thing I want to point out in this equation is that it only works for hydrogen. If you take any other atom, like helium, these equations get like really, really complicated. So RH for hydrogen is 1.10 times 10 to the 7 meters to the -1. It's not like for helium, you can just use a different value for RH for that equation, or for ionization energy, you can just use a different value for E1, or for R1, use a different value for R1. I think the instant even you go to like helium, which is just a slight step up in complexity compared to hydrogen, these equations don't work. In fact, the mathematical modeling gets like really, really complicated. You have to talk more about your chemistry teacher because the model of the atom gets very strange with energy levels when you start looking at some of these elements. They have like these like weird things that are called like, what is it, like SPDF orbitals or something like that. If you took Chem 20 AP, you might know a little bit about that. But I don't want to talk with them here. I don't like them at all. So I'm not going to make any more reference to that. We're just going to stick with hydrogen because it's nice and simple. And we have some relatively simple equations to deal with that. Those are those 4 things, S, P, D, and F. I don't know. Ms. McRory can correct me if I'm wrong. Although she can't correct me if I'm wrong because she's not here. Right. Now, we also need to take this and explain these different spectra of light. So the bright line and the dark line emission spectra. So let's look at absorption. It turns out there's two ways that an electron in an atom can absorb energy. And depending on the way it absorbs energy, things are going to turn out just a little bit differently. So one thing you can do is an electron in an atom can gain energy as a result of colliding with other high energy particles. This was the case for the Frank Hertz experiment. So in the Frank Hertz experiment, we had like an electron on the outside that we were firing, and then we had that collide with an electron in the mercury vapor. So you have two electrons, this guy that I'm firing in, and also the electron that's in the mercury. And what we noticed is that when this guy comes in, and if it hits this one, so for example, if it was 6.0 electron volts of kinetic energy, this electron in the state, the first stationary state, the ground state, will take whatever energy it needs to get up to whatever energy level is possible. So in this case, this electron, as it jumps up, takes 4.86 electron volts of energy. And it takes that exact amount because it is jumping into a very specific stationary state. And then your electron just leaves with what's left over. So in this purple one, it would transfer its energy to this one, the mercury, and then this electron just keeps leaving with whatever is left over. So let's go back here. So I've said electron in the atom, so that could be in the mercury vapor, absorbs only the amount of energy corresponding to a jump from a ground state to an excitation state, and then your incoming electron just leaves with whatever is left over. Okay, so again, electron comes in at 6.0 electron volts of EK. That's enough to get it to go to the second stationary state. So the electron in the mercury takes 4.86 electron volts, and then the electron we fired in just leaves with whatever is left over. We can also cause this to happen by firing photons at our mercury vapor. Now it's going to be a little bit differently here. It turns out the atom will only absorb photons which have a perfect match for the energy required to get to an excitation state. Okay, so let me explain this one here. So let's say, for example, that we fired in a photon that had an energy of 2 electron volts. Now, nothing's going to happen because if I want this guy to jump up, this guy needs 4.86 electron volts. So this is going to do absolutely nothing if I fire in a photon like that. So let's just erase it. It doesn't do anything. The weird thing about a photon is if you fired in a photon that had, let's say, 6 electron volts of photon energy, it turns out this guy is not going to absorb is not going to absorb this energy. And here's why. The way we define a photon is defined as the smallest quanta of energy. So I want to put in a contradiction. So let's say that this photon actually did come in. It gave this guy the 4.86 electron volts, and then the photon left with the 1.1 electron volts. Well, it can't do that because the 6 electron volts here is already the smallest quanta of energy. So for this, it's kind of like an all or nothing situation. It's either the electron's going to absorb the photon or it's not going to do it at all. It turns out the only photons that can be absorbed are ones that exactly match an energy level. So let's say that we fired in, let's do my Roy G. Biv spectrum. So we fired in like all photons of wavelengths that go from like red to orange to yellow to green to blue to indigo, violet. So we're firing in like a huge range of photons at this mercury vapor. Now, if I didn't actually fire this at mercury vapor, and what I would do if I just fired it through, like, if I didn't fire it through the mercury vapor, on a screen over here, I would just get the Roy G. Biv colors. I would get like my red, orange, yellow, green, blue, indigo, violet. So yeah, if I put it through like a prism or diffraction grating, I just get the continuous spectra of color. Now, if I fire this full wavelength range of continuous spectra of color photons, only a few are going to get absorbed. So this photon here, the one that corresponds exactly to a photon energy of 4.86 electron volts, that guy gets absorbed. What that's going to do is, because this guy gets absorbed, this is going to translate to a missing line on your continuous spectrum. If I fire in a photon that has an exact amount of energy of 6.67 electron volts, or one that has 8.84 electron volts, then same thing. I'm just going to miss a few lines of color. So the only lines of color I'm missing are the ones that match one of these stationary states. So what I'd end up getting here is if you take white light and you shine white light at an unexcited gas, an unexcited gas would mean that the electrons in the mercury are just sitting at the ground state. Only photons that have a perfect match get absorbed. They get absorbed, and then every other color passes through except for these three distinct lines, which have then been absorbed by the atom. Okay, so that explains our dark lines in the absorption spectrum. And again, if it's a photon we're talking about, it has to be a perfect match. So once again, if I fired a photon that had an energy of 9.00 electron volts, so even though that does have enough energy to get you to the second, third, or fourth stationary state, nothing's going to happen. Because again, the photon can't leave with less energy. It's already the smallest bundle of energy we're talking about. Okay, how about the emission spectrum? Well, we know this. Once atoms get excited, the electrons eventually want to go back down to the ground state. There's a couple different ways they can do this. One, they can jump straight from your excitation state to the ground state. If they do this, this will be a really big jump down. And if they make a really big jump down, it's very likely you're going to emit a high energy photon. So if it emits one photon, it's likely this one's going to fall into the UV part of the spectrum. The other thing that can happen is there can be a bunch of intermediate jumps. Like it could jump from the fourth to the third, to the second, to the first stationary state. And in this case, you're going to get a bunch of photons that are emitted, except these photons would have less energy. So I suspect this would correspond to like emitting photons would have colors of like red, orange, whatever, etc. Just the visible light photons. Or you could get the infrared photons if we're talking about like really small jumps, like if we're going from like 5 to 4 or something like that. So if I go back to this picture, so an electron, when it gets energy, it goes up. So let's say we start here. So there's two things that can occur. One, it could just make it jump all the way down. Or two, it could make it cut, in which case just one big photon, I don't want to say big photon because they're massless, but one higher energy photon's emitted. Or it could make two smaller jumps. It could do this, and then it could do this one right here, in which case two photons would be emitted. So one photon, here's another one. Now you might be wondering, and by the way, that explains the bright lines in the emission spectrum. So the bright lines are a result of photons of a specific color being emitted when they jump down energy levels. So for mercury, I've just shown a few of them here. So here's my big jump. So this one goes from n equals 4 to n equals 1. And that gives me a wavelength that's less than 400 nanometers. That's probably like UV. We have a couple of like smaller jumps. So for this one, we're going from n equals 4 to n equals 3, and n equals 3 to n equals 1. And this one, we're going from n equals 4 to n equals 2, and it's emitting 312 nanometers. That's still ultraviolet. And then, yeah, we're still less than 400. So that's, again, still ultraviolet, going from n equals 2 to n equals 1. Oh, there was one other thing, though. So you might be wondering, okay, so I'm just going to erase this. Okay, so let's say I shine white light at this mercury. And again, white light would be shining the full continuous spectrum of color from red, orange, yellow, green, blue, indigo, violet. And again, I have my screen here, which has red, orange, yellow, blue, oops, not blue, green. Green, blue, indigo, violet. And I've already identified basically 3 photons are going to get absorbed. Photons that have an energy of this, this, and this. And that's going to correspond to those 3 black lines. So you get this, whoa, that doesn't look like a line. Let's see if I can do a better job on that. Black line, missing color corresponding to these 3 photons. Now you might be wondering, okay, well, wait a second. So let's say we just fired this guy in, just a 4.86 electron volt photon. So that would cause this electron to jump up. So that's going to steal away this line right here. But wait a second, when it jumps back down, doesn't it just emit the same photon? So wouldn't that same photon just go fill back in that spot there and just cover up that dark line? Well, it would if that photon was emitted perfectly in the same direction it was being fired. Like if you fired the photon straight towards the right, and then when the electron jumped back down to the ground state, it could emit a photon back in that straight line. There's no guarantee it will. When that photon's emitted, who knows what direction it's going to go? Like this photon could go in this direction, could go in that direction. So it's unclear as to where it's going to go. It's a little bit unlikely that it's going to actually go perfectly in the straight line and just kind of fill the gap in. So that's why we still see the dark lines in the dark line spectrum, despite the fact that eventually once the photon jumps back down, you emit possibly a photon of that same frequency. Okay, last thing, Blackbody radiation curve. Again, just a quick recall of this. So this is where we took an object and we started heating it up progressively. So this diagram, I could have, this could be like a black body heated to a temperature of 2000 Kelvin. This could be one heated to a temperature of, why did I draw the period symbol there? It's temperature, not period. Okay, temperature of 3000 Kelvin. And temperature 4000 Kelvin. So what the blackbody radiation curve does is, so if we take our black body and we break it up into a bunch of like little molecular oscillators, like say it emits a bunch of electrons, there's no guarantees electrons all oscillate at the same frequency. They can oscillate at different frequencies. Therefore, they give you a wide range of emitted radiation. But what we do notice is that as you start to increase the temperature, you start to make a shift towards emitting more, like, for example, here, like your peak might be in infrared. Increase the temperature, we're shifting to emitting more photons that are emitting of a frequency that's in like maybe the low visible light range, so low VL. And then up here, it makes a shift to high visible light, maybe like low ultraviolet radiation. But no matter what you do, if you increase the temperature of this black body, you can never get anything here. Like you can't get in the high UV part of the spectrum. So it's not possible to get that. So again, this is kind of like the problem that like started like our transition to modern physics. And we'll try to do a very brief explanation as to like why we can't get this. Okay. If you look at an energy level diagram, the energy required to produce a high UV photon, it turns out, is actually higher than the ionization energy. Okay, here's what I mean by this. So this is n equals 1. This is n equals 2, n equals 3, n equals 4, n equals 5. Let's say we made the biggest jump we could. So the biggest jump we could emit would be from like 5 all the way down to 1. And we go from 5 all the way down to 1, we emit a photon that falls into the low UV part of the spectrum. Well, how could you emit a high UV photon? Well, that would mean you have to have a higher starting point. So instead of starting at n equals 5, you'd have to start somewhere like right here. You have to start here and make a huge jump down. And then maybe if I did that, I could emit a high UV photon. High UV photon. The problem is you can't, because in order to get an electron to ground state to go all the way up here to the starting point, you'd actually be giving it more than the ionization energy. So if you actually ionize the atom, you cause the electron just to leave. If the electron leaves, it can't jump down and emit a photon. So we can never actually observe any of these high UV or X-ray or gamma ray photons due to the intertransitions between the energy levels in an atom, because you would just need too much energy. You'd need too much energy to emit one of those photons, and that energy would actually be in excess of ionization. So you actually just end up ionizing the atom instead. So yeah, if the electrons leave the atom, they can't jump down. If they can't jump down, you can't produce these high frequency UV photons or X-rays or gamma rays. Okay, a lot of talking from me today to explain a bunch of stuff. So you can do something a bit more simple now, just to complete the assignment, called the Bohr model of the atom. Most of it's just dealing with a lot of the equations we were talking about in the lesson. And then in the next lecture, we're going to wrap up the modern physics unit of study by talking about a lot of really weird stuff, which is not going to make any sense, but it's actually really interesting, just because it's so, it just messes with your mind so much. But anyways, we'll deal with that then.